Welcome, everyone, to today's Explainer. We're tackling something massive today. We are talking about how to develop an IoMT-enabled smart hospital platform literally from the absolute ground up, geared specifically for the year 2026. Now, if you've been following healthcare tech at all, you already know the pieces, right? Wearable sensors, edge computing, advanced algorithms. But today, we're not just looking at the individual parts. We are looking at the complete, fully integrated architecture. Okay, let's dive into this. How do you build a hospital that actually thinks? That's the ultimate question we're answering today. We want to completely transition away from those highly fragmented healthcare systems where devices operate in complete silos. We're moving toward a fully integrated, intelligent environment. We want an ecosystem that anticipates patient needs and clinical workflows automatically without needing constant manual human intervention. To do this, we need a solid plan. So, here is our builder's blueprint for this explainer. Step 1. The Connected IoMT Foundation. 2. Building the 6G infrastructure. 3. Integrating the Epic EHR. 4. Powering with ambient AI. And finally, 5. Navigating 2026 regulatory compliance. To give you the big picture right out of the gate, here is our master schematic. This is the 5-layer 6G ISH architecture. It's kind of like a giant puzzle where every piece matters. At the very base, your physical IoMT devices are collecting data. Right above that sits the edge intelligence layer for instant local decision-making. That feeds directly into the ultra-fast 6G communication layer, which securely transports all that data up to the AI healthcare cloud. And finally, reaches the application layer, where things like remote telemedicine and smart surgeries actually happen. It's one completely unified system. All right, Phase 1, the Connected IoMT Foundation. Think of this phase as constructing the sensory organs of our hospital. We're connecting just an incredible variety of devices to the network, and this brilliantly illustrates the sheer scale we're dealing with. On one hand, you've got tiny, continuous wearable sensors like smartwatches, SpO2 monitors, and ECG patches. But on the other hand, you have massive, life-sustaining equipment like smart ventilators and infusion pumps. And all of these incredibly diverse devices, they have to speak the exact same language and flow into the same central system continuously. The practical applications for these connected devices are absolutely game-changing. We're not just talking about taking basic vitals anymore. No way. We're talking about 24/7 smart patient monitoring that triggers proactive clinical interventions the literal second a heart rate flatlines or fluctuates. We're using real-time location systems, or RTLS, not just to find a lost wheelchair, but to instantly locate life-saving emergency equipment, or, crucially, to prevent a dementia patient from wandering off. We've got smart e-ink displays at the bedside that sync instantly with online records to prevent handwriting errors, plus highly sensitive IoT sensors ensuring strict cold chain compliance for vaccines by monitoring fridge temperatures around the clock. As a builder, your whole goal is ensuring these massive data streams trigger automated, life-saving actions seamlessly. Moving right along to Phase 2, building the 6G infrastructure. Now, we need a way to transmit all of that massive data instantly. We literally have to upgrade the hospital's central nervous system. You might be wondering, well, why not just use our current 5G networks? And 5G is fantastic, but it maxes out at about 5 to 10 milliseconds of latency and around 10 gigabits per second. For critical tasks like remote robotic surgery, where a surgeon is operating from miles away, a 5-millisecond delay can be catastrophic. The 6G HIS edge architecture brings that latency down to under 1 millisecond, pushes data rates over 100 gigabits per second, and offers this unbelievable 99.9999% reliability. It's that sub-millisecond responsiveness that makes the true future of the smart hospital genuinely viable. Now, what's really interesting about this slide is the energy aspect. You'd naturally think that upgrading to 6G and doing all this advanced processing would drain device batteries so much faster, right? Actually, scratch that, it's the exact opposite. Because we're intelligently offloading the heavy computational lifting to the edge intelligence layer, putting it closer to the data source, the actual IoMT devices consume significantly less energy. We are talking about up to a 30% reduction in energy consumption for things like wearable sensors, allowing them to run much, much longer without needing a recharge. All right, let's look at Phase 3, integrating the Epic EHR. So, we've got our high-speed network. Now we have to securely connect it directly to the hospital's central brain, the electronic health record. Here's the actual step-by-step workflow for getting a digital medical device safely talking to an Epic system. First, device configuration, setting up your HL7 or fhir protocols right on the hardware. Second, Epic bridges prep, creating that new external system record in Epic's dedicated integration module.
Third, interface engine setup, using centralized engines like Cloverleaf or Mirth to map and transform the device data into EPIC-compatible formats. Fourth, locking the whole thing down with security like TLS encryption and OAuth 2. And finally, rigorous data validation, just to ensure the vitals showing up on the device perfectly match the patient's digital chart.
Now, if that integration process sounds incredibly labor-intensive, well, historically, it really has been. But here's the so what. By utilizing a cloud-native iPaaS, which stands for Integration Platform as a Service, healthcare organizations are seeing a massive 60% reduction in integration deployment time compared to those old traditional methods. By using reusable connectors and automated deployment pipelines, onboarding new medical devices becomes radically faster and totally eliminates those frustrating data silos.
Next up, Phase 4, powering with ambient AI.
This is where we breathe genuine intelligence into the infrastructure so it automatically operates. Think of ambient AI as the subconscious brain of the hospital. It's context-aware, ubiquitous, dynamically adaptive, proactive, and seamlessly interoperable. Instead of a doctor having to sit down to explicitly type notes into a computer or manually query a database, ambient AI runs continuously and quietly in the background. It observes the environment, it understands voice commands, it monitors live vitals, and it anticipates risks, like, say, a sudden drop in blood pressure. And it does all this without demanding any explicit human interaction to trigger its analysis. It just silently works to support the clinical staff. And finally, Phase 5, navigating 2026 regulatory compliance. Look, you can build the most technologically advanced hospital in the world, but if it doesn't adhere to strict international building codes, it will literally never see a single patient. If you're building in Europe or for the European market, you absolutely have to look closely at this timeline for the EU AI Act. We're operating right now in the critical lead-up. By August 2026, these stringent obligations for high-risk AI systems become fully applicable. That deadline is literally just months away from today. And by August 2027, all transitional arrangements for legacy systems come to a hard stop. Because healthcare AI directly influences patient safety and diagnosis, it naturally falls straight into that high-risk bracket, and compliance is just non-negotiable. So, the crucial point is how regulatory bodies actually classify these systems. Over in the US, the FDA evaluates software functions based entirely on risk. If your software, let's say an AR or VR surgical image tool, fails, but there's no probable risk of serious injury to the patient, it requires basic documentation. But if you have an AI-driven sepsis alarm in a critical care environment and a failure means a probable risk of death or serious injury, you immediately jump to enhanced documentation. The classification is inherently tied to the probable risk to the human being.
To sum up this whole complex regulatory landscape, the AI Act doesn't just replace existing device regulations like the MDR or IVDR, it adds an entire complementary layer. Regulators do not view AI as simply advanced software anymore. It is now treated as a regulated, high-risk system that requires structured, continuous lifecycle oversight. As builders, you've got to prove exactly how the model makes decisions, how it handles data governance, and you have to prove there is meaningful human oversight continuously in the loop. Which leaves us with this final, honestly pretty provocative question. Can our regulatory frameworks and security architectures adapt as fast as our smart hospital networks are evolving? We are rapidly pushing the boundaries with sub-millisecond 6G and invisible ambient AI, but human safety protocols inherently require rigorous, friction-heavy validation. Balancing that breakneck pace of technological innovation with the absolute necessity of patient safety, well, that's going to be the defining challenge for smart hospital builders in 2026 and beyond. Thank you so much for joining me on this explainer. Keep building, and I'll see you next time.